Applied optimization, section 4.5. So how do we solve applied optimization problems? These are problems where you want to minimize the cost, or maximize profit, or minimize the use of raw materials to manufacture a product, and so on and so forth. The first thing we need to do is read the problem, and you make sure you understand it. Find out what's given, and then what is the unknown that you want to optimize. In other words, what is the unknown that you want to minimize? It could be the volume, surface area, and so on and so forth. Draw a picture. Label any part that may be important to the problem. And then you got to introduce variables. List every relation in the picture and in the problem as an equation or algebraic expression, and then you identify the unknown variable. Now this is the most important thing. We got to write an equation for the unknown quantity. If you can, because sometimes the unknown quantity that you want to optimize is a function of more than one variable. So if you can, we got to express the unknown as a function of a single, that's important, single variable, or in two equations in two unknowns. This may require, like solving systems, or most of the time it's like we do substitution. So we substitute a given, a given quantity in terms of the other variable, so that what you got is an equation in one variable. Test the critical points. And what are the critical points? Whatever you set the derivative to 0, first derivative to 0. And then the endpoints in the domain of the unknown. Now remember, these values should make sense, because you can't have like a negative length and so on and so forth. Use what you know about the shape of the function's graph. Use the first and second derivatives to identify and classify the function's critical points. So once you get a critical point, take the second derivative, plug in the critical point, and then if it's concave up, then you've got the value of the variable minimizes, or if it's concave down, the value of the variable maximizes the quantity. An open box is to be made by cutting small congruent squares from the corners of a 12 by 12 inch sheet of tin and bending up the sides. So how large should the squares that are to be cut from the corners to make the box hold as much as possible? So right here, when you say if you want to find out how much that the box will hold as much as possible, that means it has to do with the volume of the open box. Right, so here's the picture. So it says we gotta find a 12 by 12 tin, okay, and then you cut a square on each corner. The question is, how much do you cut off so that when you fold up this box, then you maximize the volume? So once you folded up the box, like this one, folded up the sides after you've cut the corners, notice that this is now the length, which is the same as the width, would be 12 minus 2x, because there's one x and another x on both sides. So this length from here to here would be 12 minus 2x. Same thing there. And then when you fold everything up, then you create an open box. And what is the volume? The volume is length times the width times the height. So now, after you've folded it up, x becomes the height of the box. Right? So let V be equal to the length times the width times the height. And the length is, as we said, 12 minus 2x. If we let x be the height of the box, then that means our volume becomes length times width times the height. Right, so if we FOIL everything here, so here is just pulling out 2. So once we pull out 2, we get 6. Pull out 2 here, we get 6. So that's where the 4 comes from. Then when you square it and you distribute the x, then this is the quantity, the volume, the equation to volume that we want to what? What is the goal? We want to maximize the volume. Okay, so the first thing we do here, it's already a function of one variable. It's a function of the height of the box. Alright, so take the first derivative, which is 36 minus 24x plus 3x squared. Set it equal to 0. And that's just pulling out the 3 from each of these. And so that's why this becomes a 12. And when you factor this, you're going to get 6 minus x and 2 minus x. So the two critical numbers are x equal to 2 and x equal to 6. Now the thing is, if x is equal to 6, what happens to the box? Well, if you cut off too much out of here, there won't be a box, because you know, if x is 6, that cuts all the way through, the halfway through the sheet, so you won't be able to create a box. So your x has to be between 0 and 6. And that's why we're going to try x equal to 2. So what do we do next? Take the second derivative. Alright, so after you take the second derivative, it's from here. We plug in, when we take the second derivative out of here, then you get minus 8 plus 2x. And then what do? We use the second derivative test to test whether x equal to 2 maximizes the volume. So if it does, what do we want to expect? You want that v double prime of 2, when you plug in 2 in here, you want it to be negative so that it's concave down. Alright, so let's plug in v double prime of 2, and that's obviously negative because that's minus 8 plus 4. It's going to be negative 48, so it is negative. So that means x equal to 2 maximizes the volume. So here is the graph of the function v, which is in this case we let it be y, you know, the volume y is equal to x times 12 minus 2x whole thing quantity squared, and you see that it attains a maximum at x equal to 2. You have a line tangent. So a line tangent there is 0, is a horizontal line. That's why y prime in this case, or v, y prime at 2 is 0, and then y double prime or v double prime at 2 is negative. That's why it's concave down. So you have a maximum occurring at x equal to 2. Okay? Like we said, you read the problem, draw a picture, introduce variables, and in the second example we're going to have, when we write an equation of the unknown quantity that we want to minimize or maximize, we're going to get the next problem. It'll involve two variables. So this is where we have to express the unknown as a function of just a single variable, that whatever we want to minimize or maximize, and test the critical points and endpoints. Okay, so let's go ahead and look at this problem. You have been asked to design a 1-liter can shaped like a right circular cylinder. Right, so this is how it looks like. Okay, so what dimensions will use the least material? So when you say least material, that means how much material you're going to use to create the can. Alright, so suppose this is h and the diameter is twice the radius, of course. So how does that gonna, what do we want to, first of all, what's given? If this is 1 liter, what is the volume therefore? That would be 1000 ml. Okay, so the volume is pi r squared times the height equal to 1000. That's given. So that's kind of like a constraint in some ways. It has to be a 1 liter can. Now what do we want to minimize? The surface area. Now you've got you've got the bottom lid and the top lid. Now what is the surface, what is the area of these two circles? It's pi r squared, so there's two of them, that's why there's the 2. What about the side of the can? If you think about it, if you lay that out, suppose it's still, if you cut through here and you lay it out, you get a rectangle with width, and the length is really the circumference of the circle. So that's why you have, what is the circumference of a circle? 2 pi r. And then the width is h. Okay, so what is the next thing we need to do here? First of all, area is a function of radius and height. So that's when you have two variables. So let's go ahead and solve h in terms of what? Solve h in terms of r using this given equation. Alright, so let's see. We solve for h in the equation pi r squared h equal to 1000 ml. So solving for h, that's dividing everything by pi r squared. It's going to be 1000 over pi r squared. This h is going to be substituted here. So you're going to get a equals 2 pi r times what? 1000 over pi r squared. And that just, and then plus 2 pi r squared. And as you can see, that's going to be 2000 because you multiply 2 by 1000, and then this cancels out, and then one of the r's remain at the bottom. Okay, plus 2 pi r squared. So this is now the quantity that you want to minimize. So what do we do next? We take the first derivative. So a prime would be, remember this is the same as 2000 r to the negative 1. Because don't forget, it's easier to do it that way than doing the quotient rule. It's just use the power rule. Plus 2 pi r squared. So now when you take the first derivative, it's going to be negative 2000. R to the negative 2 means over r squared. Okay, plus 4 pi r, because you would bring down the 2. Okay, so here you taken the derivative of a with respect to r. And then what's the next thing we do? Set it equal to 0, because that'll give us the critical point. Alright, so you've got, take the common denominator, so it's going to be r squared. Then you're going to get minus 2000 plus, that's over 1, so what's the common denominator? R squared. You need to multiply that by r squared, so you have 4 pi r cubed. Set it equal to 0. Now remember, we can't let r be equal to 0, so r cannot be equal to 0. Right? So we just let minus 2000 plus 4 pi r cubed equal to 0. Okay, so what is that? That's going to be, put 2000, so you have 4 pi r cubed equal to 2000. Okay, let's continue to the next slide. We have 4 pi r cubed equal to 2000. Divide both sides by 4 pi. And so we have r cubed is equal to 500 over pi. So r is the cube root of 500 over pi. Now, going back to what is our first derivative. It was minus 2000 over r squared plus 4 pi r. So let's go ahead. So v prime is minus 2000 r to the negative 2 plus 4 pi r. So take the second derivative, it's going to be positive 2,000 or 4,000 rather over r cubed plus 4 pi. So remember, we are differentiating the volume with respect to the radius. And then after this, we take v double prime, substitute it for the cube root of 500 pi. The cube root of 500 over pi. So all we do is just take 4,000 divided by, now because you're taking the cube root of a cube, that's just 500 over pi, okay, plus 4 pi. Now regardless, the point is, what is this number going to be? It's going to be positive. So because it's positive, we know that r equal to the cube root of 500 over pi minimizes, okay, because remember, if it's positive, it is concave up. And we always put a smiley face, so remember that it's concave up. So it minimizes the area. Okay, so what is the height? Height is 1,000 over, let's go back, 1,000 over pi r squared. So 1,000 over pi r squared. So we'll just have to multiply, or rather substitute. It's going to be the cube root of, we'll multiply by pi here, 500 over pi, and then that whole thing is squared, right? So how do you rationalize the denominator? Then you multiply both the top and bottom by the cube root of 500 over pi divided by the cube root of 500 over pi. Why did I use the cube root? Because there's already a squared term here, so all we need is just 1. So it turns out that this becomes 1,000 times the cube root of 500 over pi, okay, divided by, what is this? Well, that takes care of, it's going to be pi and times 500, right? Because over pi, because you took the cube root of the cubed of these things. Once you combine the two together under one cube root sign, that's going to be cubed. So it really, that's what really our goal was, to rationalize the denominator. So cancel that, and so 500 goes into 1,000 twice, so you have 2 times the cube root of 500 over pi. So basically what it is that the height is twice the value of the radius. And if you have twice the value of the radius, then that also minimizes the area. So these are the dimensions. That's the radius and that's the height. So as you can see, here is the length of r. So a is a function of r here. And you have a zero derivative, and then it's concave up because the second derivative of a, if you substitute this, is positive. So that makes it concave up. So it minimizes the surface area. Here is just how it looks like, that if you had it too tall, then that uses up more materials. Same thing here, it uses up more lid and the bottom. Okay, so the most ideal situation is that if this is the area, if this is the length of the measure of the radius, the height has to be twice the radius.